Okay.
Many of you may recognize our guest speaker today. He most recently served as interim head of AE for us. Shortly after he was relieved of that role in spring of 2020, Professor Elliott was approached to be part of a team working on developing an emergency ventilator known as Illinois RapidVent in response to the coronavirus pandemic. He is described by his colleagues on that team as a fluids engineering superhero. So here to tell you more about the process of creating this life-saving device is Professor Greg Elliott.
Great. Thank you very much, Courtney, for that introduction. And I wish they would stop saying that and putting that in publications, that comment. So anyways, yeah, so it's a real privilege for me to be with you here today. And just kind of, I'm going to describe a little bit of the Illinois RapidVent. I just want to recognize the project leader who did a fantastic job was Bill King from Mechanical Engineering. And then you'll see whenever I show the breakdown, basically the engineering and test team that I worked with, there were about 40 people that worked on this project, over 40 to 50. But the people that, a lot of the work that I'll show you today, Stefan, he's a research scientist here at University of Illinois and also with CTS. He was one of the leads of the engineering testing team that I worked most closely with. I actually had a key to their building for a while. And then also Blake Johnson, Sam and Tong Hoon from Mechanical Engineering are professors there. And then Andrew is also a engineer out at CTS. And I just want to recognize them. They're the ones that I work most closely with. So what this is going to be, let's see, this is basically a case study from my point of view. So I'm going to give you a certain outlook on the RapidVent. I'll describe how it works, but really what I want to kind of describe is just the process of a really exciting project I got to work on. So basically what had happened is back in February, at the end of February, I had this wonderful privilege of relinquishing all of my responsibilities as department head to John Friend, who's joining us here today too. And so I thought I would be on easy street after that. And then after that, that I felt all of this relief and relaxation, the next thing I find is that I received this email, which was quite urgent, which you don't get from the dean's office all the time. And basically, this was back on March 13th. They had invited me to be part of a team. And this was, you can see it's Friday late, something like 11:30 p.m. To be on a team, really to respond to a need that had been, we've been made aware of by doctors at Carle Hospital. And you really don't receive something like this in your career very often. And basically, if you hearken back to that time, they were looking at this outbreak of COVID, looking at some of the things that were happening in places like Italy, even New York City, and had some quite concerns as far as what that impact would be like in this community. And I know that things have changed, some of our responses there as far as the constraints and the shutdown have alleviated this. But back then, basically, the hospital felt that some of these projections were looking quite dire, that we would need 400 additional ventilators just in our region. And so they had approached the College of Engineering and then reached out to John, and John had suggested my name to them, which was quite a privilege to be able to be tasked to work on this project. And so after that, so that was Friday at about midnight. The next day, basically, my first response was, what is a ventilator? So that's the first thing I wanted to look up. And so you go to the web, and just for your understanding, it's basically a machine that mechanically assists your breathing. So most of these devices are designed in such a way that the person can either be out as far as unconscious, or they can even be through medication placed into a slight coma, so that these ventilation devices are actually wanting to breathe for that person. And basically what we want to do is control things like the breathing cycle, the breaths per minute, the time of inhalation, so the time we take in that breath, the exhalation time. And then also, particularly in a hospital setting, these are all the new words and acronyms that I learned during this time. We want to be able to control what's called the peak inspiratory pressure. And so if you look at that graph, basically that's the peak pressure. And this is giving a graph in centimeters of water is what they usually measure this in. But they want to be able to control that peak inspiratory pressure. And then the other pressure that they want to be able to control with these devices are the positive and expiratory pressure. So it's kind of that pressure that at the end of the breathing cycle, whenever you let out a breath, they want to be able to control that pressure. And that's so that for someone that has some trauma to their lungs, you want to sometimes elevate that pressure so that they can more oxygenate the lungs and the bloodstream. The other thing that you want to be able to control is what's called the fraction of inspired oxygen. And so that's basically, you want to go from a pure 100% oxygen as far as what the patient would be breathing in, to also mixing that with air so that that percentage is actually less than 100% oxygen. If a patient is on oxygen for over 24 hours, they start to, the acidity in their lungs start to build up into a condition called acidosis. So that can start to actually destroy some of the lung tissue. And then also there's additional breathing controls that a ventilator wants to have. You want to have safety controls there. You want to have the operating standards to be able to plug into the different devices, the filtering devices that the hospital has. And so so that was day one for me, just finding out what a ventilator is and hopefully expressing that well to you too. The second thing we wanted to do is basically in this first week, and this was done primarily by Bill King, and also Fast Radius was a rapid prototyping company that we worked with. And we really looked at possible ventilator solutions early on. And I would say within that first weekend, we kind of went through and made this decision. And basically, you can go through electronic computer-controlled ventilators. We were looking at providing 400 ventilators within 3 weeks. And so it was quite clear that we wouldn't be able to get FDA approval for all the components that were in that type of ventilator. The other thing that you can do is look at manual handheld ventilators that you might have seen on movies, or hopefully you've never seen one of these in person. But the MIT did an approach where they actually took one of these handheld ventilators and then tried to wrap a box around it to be able to automate that squeezing process that you would do with your hand of the ventilator bulb. And we decided against that the complications with that, and it might not be something that people could walk away from and not monitor continuously. And so what was really decided is to look at a gas-driven emergency transport ventilator. So these are ventilators that are meant for crisis situations. They are also used for transport. So whenever a patient's being transported from one floor to another, they would use one of these ventilators. The advantage of this is there's no electric. It's actually driven by gas. For us, there's a low part count so that we wouldn't have to build and design a lot of part, and it's easily manufacturing. Almost all of the parts except the springs in this system and maybe the rubber diaphragm, but we even built that with rapid prototyping. But other than the springs, all of the parts you could build with rapid prototyping. And we had a good example that exists. What I would call our reversed engineer example was a product called Vortran go-to vent. And so we learned a lot by taking these apart, even ordering them on eBay and looking at some of these and ordering them and over the course of the project and testing that our device would actually meet the performance of the device that's already out there. And so we learned a lot by just reverse engineering, and you'll see our device looks very similar to theirs. The other thing that happened within that first weekend, I credit Bill with this, is just really building a good leadership structure. These are all of the different categories that we had for people. The leadership team consists of Bill King, Harley Johnson, and the dean from the Graduate College of Engineering, medical doctor from Carl, and then also Tech Mill, some expertise from a local manufacturing company. Over 40 engineers, doctors, medical professionals, and manufacturing experts actually came together on this project. So that organization was really important. Where I stepped in is basically I was part of the engineering and test team and also the animal study team, which was actually quite a bit of fun for me, having never done that before. So let me just go over just real quickly in a few minutes, just really what this device is. So the first prototype test was March 22nd. That's Stefan that's shown there. And I'll just briefly play this video. This was actually
we have good news from the test bench.
We're
evaluating the first rapid prototype part. We have the following configuration. We have a rapid prototype modulator. We have HEPA filter in line, the way it should go. We have rapid prototype TP. We had a little bit of a leak with the check valve. We sealed it temporarily with some sealant stuff. So this fixes it for now. We have the moisture filter, so everything is the way it should be later in operation. We have removed the inlet cap, which means we are in training right now, 50%, so we have FEOI 50. And this explains a little bit of the entrainment noise we hear. If you look at the data, we have right now very regular cycles. We have an inlet pressure of 50 psi. We have a tip of approximately 30 and a peak of 10, which means we operate at a 3-to-1 ratio, exactly as we want it to be. If we see the flow rate, we have peak volume flows of up to 40 liters per minute. So also this is within range.
So that gives you an idea of our first prototype test. And I will say, in working with Stefan, most of the time that is the shirt I saw him in. So for the first week. So basically we went from, getting an email on March 13th, having the leadership organized by March 16th, and had a working prototype by March 22nd. So it was really exciting to be involved in this kind of project that is really neat to be involved in something, working with some fine individuals, doctors, and also other engineers. Let me just describe a little bit about what this RapidVent is. So the RapidVent basically was designed so that we went over to the hospital, we looked at the kind of oxygen supply that they had, so designed it so that it could be incorporated into many of the rooms, not only the ICU rooms that had 50 PSI of oxygen available. Then there's some filters that they always want to put on. And then usually you could use this. Most likely this would be used with an intubation tube, but it's shown here with a mask. And what we wanted to control then is basically the breaths per minute, and then also our pressures, the PEEP and PIP ratio, to be able to control the breathing pattern. This is the device that we ended up with. This is pretty much the device that was the final device, maybe not the final CAD that we had. It's broken down into 3 sections. We have the patient T, so that's the location where we hook up to the oxygen supply and to the patient. Manometer, that's just a simple pressure device that you can look at and see what the PIP and PEEP pressures are, and then the modulator, which was something that I was put in charge of on the project. So basically, for the patient T-sub assembly, there's a breathing tube that fits up to the oxygen tube, or the tubes that the hospital already uses, that connects to the patient. There was a one-way flapper valve that we designed into the system. This was so that if the patient took a breath spontaneously, that they would have some gas. If it wasn't the oxygen supply, it was room air that would be supplied, so that they didn't have a restriction in their breathing. There's also a pop-off valve, so that if a mistake was made and too much pressure was put into the system, that it would pop off and not harm the patient. And then also we have an oxygen adapter that is basically an ejector that can take 50 PSI of oxygen in, and then set the flow rate, or the flow into the device, the pressure into the device. And then by removing that, then you can change the percentage, this FiO2, which is the percentage of oxygen. So the green device, when you install that, then it's 100% oxygen. When you remove that, then you're getting about 50% room air also through the device. Then we have the manometer, and this is just the analog pressure gauge, spring-loaded, just so that you could monitor that the device was working properly and monitor the PEEP and PIP pressures. And then the modulator. The modulator, what it does is it does two things. It allows you to set the breathing cycle time, so the inspiration time and the exhalation time, through the rate dial. And then also it allows you to control the PIP and PEEP pressures, so through the others spring-loaded. Now, the way that the logic of this device works, it's pretty clever, the way that these devices work. Basically, what you do is you're pressurizing this tube, and you're pressurizing the patient's lungs. And as that pressure builds up, then the diaphragm is closed, but you've set it with a spring tension. And so when you get the pressure high enough with the area that overcomes that spring tension, then that diaphragm opens. The pressure flows out into a chamber that is pressurized, and so that pressure acts over a larger area, so that diaphragm stays open. And then out of the rate dial, the oxygen air gases are actually exhausted into the room. And so that it's basically a needle valve that you're opening up, and that controls how long it takes in that breath cycle. The testing that we did for this device, we actually had it over at CTS. We set up about 10 of these devices that had these test lungs that were hooked to them, flow rate control, and monitored these. There was one of our devices, we had over 1 million cycles in. And so we did endurance testing just to make sure that the device would work for several days, up to a week, without failing. And I don't think we had any of them fail. Every once in a while, we would have to readjust some of the rate adjustments, but otherwise they performed very well. Our final design did. And then the most fun for me, I wish I could show you videos of this. I haven't been allowed to show videos of this, but we did animal testing. And so we went out to the vet. There's a pig farm here that we had about 3 vets there to monitor the pigs. We actually gave them anesthesia, put them out, and then we tested this device on them, and we would measure, we would draw blood about every 3 hours, measure the CO2 levels, measure the oxygen levels of the breathing. We actually did a few of these tests. These were so useful, and discovering things about the device. Our first test, actually, we're starting to have problems with acidosis in the pig, and there's quite concerned with that. And they allowed us to do one last test, which was really good. What we had found is that we had too long of tube there, and so whenever the pig wasn't able to totally get rid of the CO2 in their breathing, we shortened that tube up, and the device really just was flawless. Really worked well and was able to operate over 24 hours without a problem. The doctor was there from Carl and could even tell us, what rate she wanted, and we were able to meet that with the device. So kind of where this is at now then is the University of Illinois set up a non-exclusive technology agreement. It's free. And so basically this package contains all the working principles, bill of materials, all the CAD of the device, all the summaries of the animal studies, and also how to assemble these, and also information for filing with the FDA. So the project lasted about a month before we got a package together that we could actually put out. As of today, there's been 71 signed license agreements all over the world. They've requested this. We've been contacted by at least 5 organizations that have working prototypes, and they've sent us back films of those, and then videos of those. Belkin is probably the one that's most well known. It was reported in USA Today, so I'm allowed to share that. But they're planning on commercializing this. They call the device FlexVent, and so that's what they're doing now. So with that, kind of gives you some insight on a project. I mean, it's I'm definitely not happy of what caused me to work on this, and a pandemic, that's affecting our country and the world, but definitely exciting to be able to work on a project like this. Great engineers that I got to work with, learned quite a bit in the process, and able to do some good work. So with that, I guess if anyone has any questions, I'd be happy to answer that. I went over a little bit of time than Courtney told me. 20 minutes instead of 15, so close. But yeah, if anyone has any questions, I'd be happy to answer them if I can. Let's see.
I have a question.
Sure.
Hey, so I don't know much about this, right? But one of the concerns with the ventilators at the beginning was how do you control them? So pressure control, volume control, and what do you do with several patients? So I don't know how disparate were the peaks that you tried them in. So having different lung resistances and meeting different pressures because your lungs are damaged, right? Yeah. So is that the role of the modulator? I'm not sure I got it completely, but how do you, so you set it to the maximum pressure of the worst of the patients, and then everyone can draw a different one? How does the pressure diagram in here kind of high level works?
Yeah, so let me go, let's see if I can go back here. Yeah, so how the device works, so basically you're setting this spring tension, and so we did try that. So in the pig studies that we did, we actually would take a pig and we would put, and this is a typical thing you do for breathing studies when you're using animals, is we put 40 pounds of sandbags on the pig laying on its side, and so then it labors their breathing. And so then once that was done, then you would need more pressure to expand the lungs. And so we're able to show that by dialing that down, you can. And so as you can see, what we're doing is that blue dial that you see there, what you're doing is compressing that spring more. And then it takes a higher pressure than a higher pip to actually make that diaphragm then go off of the tube. So that's how you set that pressure. Yeah. Did that answer your question?
Thinking about it. No, I mean, I was really like I remember to hear a lot about that when the discussion came right back in March, like whether or not it's safe to put multiple patients on a ventilator or not.
Oh, yeah.
Different requirements of volume and pressure that each person might need, no? So they were only allowed for emergency situations when you can hook up different patients that are similar in complexities, right? So I'm thinking on that.
Yeah. Yeah, I mean, you know, there were as far as hooking up multiple patients, basically, the way that this was designed, because we had an ejector on it, you could put, as long as you have 50 psi of oxygen to the system, the system will regulate itself, because you've got a choke flow through an ejector there. And so as long as you're supplying 50 psi, that's all the device cares about. Some of the early I think our earliest ones, we didn't quite have the ejector. Actually took us the longest to get that designed appropriately. And if anyone's ever designed ejectors, they're kind of finicky because you're drawing in air, and then you're also trying to choke the flow. And so once we got that right, pretty much, you know, you just need to make sure that you had a consistent 50 psi. You didn't have to control the flow rate into the device as long as you had 50 psi into the device. So.
Okay. Thank you.
Sure.
Cool.
And yeah, it was pretty neat. Any other questions anyone has?
Hey, Greg, this is Dan Bedoni.
Yeah.
Thanks for the detail. I have a question about the age of patient that can be hooked up to this. Is it targeting adults? Is it appropriate for pediatric users?
Yeah, so I don't know. It was targeted for adults. Yeah, so definitely there was a minimum PIP that we could control with the device in the springs. And I think I do remember the doctors saying that we wouldn't be able to put pediatric patients on this. Yeah, because, and that's, you know, I think you could probably have multiple springs and be able to do that. But I know that with our range, we weren't able to get it to work in the range of pediatrics. Yeah. That's a good question.
Thanks a lot, Greg.
Yeah, sure. Any other questions?
Well, if there are no other questions, I think that's about our time for today. So thank you, Greg, for giving that presentation for us. I know we had a lot of interest here, and I think it's just a fantastic thing that you worked on. So
yeah, thanks. Thanks for the opportunity. Really enjoyed it. Yeah.
All right, and thank you to everyone else for joining us today. We'll have another one of these talks next month, so be watching your email for that.
Okay. Have a good day, everybody.
Thank you, everyone.
Join us. Yep.
Thank you.